Welcome back. I'm the Tutor Wizard, Adrian. Please subscribe right here and hit the notification bell. You get notifications for this series and a bunch of others. Today we're doing multivariable calculus. We're in chapter 1, which is partial derivatives. Specifically, we're doing section 1.7, which is extreme values and saddle points for functions of two variables. This lecture, what we're going to do is we're going to do the definition of local max and mins for a function of two variables, saddle points for two variables, technically critical points of two variables. We'll do Fermat's theorem or the first derivative test for functions of two variables, and we'll do a couple of examples. Let's get to it. Okay, to start off with, we'll do local max and mins, and then we'll get the saddle points. To do local max mins for a function of two variables, we mimic again what we're going to do for a function of one variable. For a function of one variable, one of the major applications of actually having the first and second derivative, not to torture first-year students. I know, it is a good application of making you, first and second derivatives, try this one, but that's not the major applications of what we're trying to do here. We're trying to use those to sketch the curve graph of f. Once I do that, I can find, in particular, use the first derivative to find local max mins and intervals of increase decrease for a function of one variable. We want to do exactly the same thing here. I want to, for a function of two variables, use the first and second order partial derivatives to sketch that surface, but in particular I want to use the first partial derivatives to help me try and find, and in this case we're actually going to have to use the second partial derivatives to find out where local max, mins, and saddle points are. Let's give the definition of local max, min, and saddle point. Alright, the technical definition for a function f(x, y) of two variables, we say that this function has a local minimum at a point AB if f of AB is less than or equal to f of xy for every xy in the ball of radius delta around AB. In English, that has that one word, basically, near. Near is what I mean. If xy is near AB. What does near mean? Mathematically, it means this. It means this. AB, ball with radius delta, x is near. We're like, near is too vague for us, so we would like to have an analytical, thank you, Cachet, for this notation. Near. A local maximum at AB if f of AB is greater than or equal to f of xy near AB. And we're going to switch from what's the difference between local and absolute, other than the word. Here we change from near to in the entire domain. So you're an absolute minimum. Just like in one dimension, x squared has an absolute, well, not the axis is rectilinear, the parabola is curvilinear. X squared, the graph of it technically, has a local minimum at 0, but it's actually an absolute minimum also because in its entire domain, that's the lowest point you can get in the range. You can't go lower than 0. So the same thing for a function of two variables. We have an absolute minimum if that point is less than all other points on the surface, or all the points in my domain now. Let's do Fermat's theorem for local max, mins, and critical numbers in two dimensions, and then we'll give the definition of saddle point. Saddle points are not these guys. Okay, Fermat's theorem for a function of two variables, or commonly referred to as the first derivative test. Pierre de Fermat was a French lawyer in the 1600s, and it was classic for taunting. He was extremely brilliant, and he was an amateur mathematician. He liked to prove things and then send the results without the proof to the English and say, look what I proved and I have this result, can you prove it? One of them was what he's saying in one dimension. In one dimension, if a function f of x has a local max or min, in one dimension, there's my antecedent, then the conclusion of that statement of Fermat's theorem in calculus, he's got a bunch of them. If I have that the function has a local max min there, what's the conclusion? Then the derivative at that point, a, is 0. So f of x at a. This is confusing because this now gets into the four classical statements of logic. Every time I have a declarative statement, I have the direct statement, I have the contrapositive, I have the inverse, and I have the converse. The converse of this is false. X cubed is the classic example that we're going to do in a second for one dimension. But what we're saying here is just because the derivative is 0 you're using the theorem wrong. The converse is false. You can find functions where the derivative is 0 at the point, but the point is not a local max or min. What Fermat's theorem is going to be used in one dimension is, what it says is, our strategy will say that it doesn't tell us exactly where all the max mins are. Just because the derivative is 0 doesn't mean you have a local max min there. But if you are not a local max min, your derivative will never be 0. And if I take the contrapositive of that, says if the derivative is not 0, then you will not be a local max min. So the contrapositive tells me if the derivative is not 0, you never hope to have a local max min for your function there. But the converse is false. So just because your derivative is 0 doesn't mean you have a local max min there. What? You use an example, x cubed. X cubed is this function. That's actually the graph of x cubed, but I'll cheat. X cubed. Then at 0, how do I know that? Well, if f of x is x cubed, then the first derivative of x is 3x squared, which is 0 if and only if x is 0. So my derivative is 0 doesn't mean I have a critical number or a local max min there, because when I check, I still see that I'm increasing in and I'm increasing out. Why? Because my derivative is positive globally everywhere. So when I make a table and I actually check, this function has no local max mins, no absolute max mins, and it's monotonically increasing on its entire domain for functions of one variable. We're now doing this for functions of two variables. What does that say for us? The first derivative test for a function of two variables. If f of x has a local max min at a point a, b now, then the partial derivatives of f with respect to x and y are both 0 at that point. So it's giving us a complete analog to Fermat's theorem in one dimension. What does that now say? Be careful. If the derivatives are 0, doesn't mean you have an absolute max or min. You could have the third thing, which we're going to call a saddle point in a second. Let's give the definition of that, and then we can use the terminology for critical point. An interior point. Also, what's an interior point? If I have a set like this, any point which has a ball around it entirely inside there is an interior point. That guy's a boundary point, or this is an exterior point. Point set topology, it bothers me. Interior point. If you have an interior point of your domain, we call this a critical point if the first and second derivative are 0 there, or if the first order partial derivatives do not exist there. This is our definition of critical point. Rephrasing that, having this definition now, what does the theorem say? If you have a local max min there, then you have a critical point, because both the derivatives will be 0. What that says is, just because you have a critical point doesn't mean you have a local max min there, but there will never be a local max min at non-critical points. This is why they're calling them critical points. What's our strategy for finding these critical local max mins for a function of two variables? It's the same thing as for one variable. I find all the critical points. I find out all points where my first and second or my first order partial derivatives don't exist or are 0. And then I check them all to see, there's going to be a different scenario. We're going to have to check that in 2 dimensions. But then we check at each one to see whether we have a local max or a local min. And then we decide from that. What's the third case we could have? Just like x cubed didn't stop increasing or decreasing, we can have functions that are monotonically. So even though this was a critical number, it didn't have a local max min there. When this happens, we're going to call that a saddle point. Let's do that next. If we have a differentiable function f of x, y, we call a critical point AB as a saddle point for this function if in every open disk we have basically the negation of what a local max or min is, not a local max and not a local min. What does that mean? It means that there's some points in every open disk centered at that point AB. There's points that I can find which have values less than AB, f of AB, and points where I find where they are. Did I write them both the same? No, f of AB is less and f of AB is larger. Okay, good. Flip those around. We also call the corresponding point AB, f of AB, on the surface. We call that the saddle point of the surface. Let's do an example of that specifically. All right, example 1. We're going to find the extreme values for this polynomial of two variables, x squared plus y squared minus 4y plus 9. I feel a completion of squares coming on somewhere. How do I do this one? We have to argue, but the tricks are always the same. The mathematical discourse is different. Now we're in functions of two variables. All the tricks I'm going to use are the same probably. First of all, I broke it into pieces for us, and then I'll do the last step for us. But here it is so that we can see. If you don't have this and you're doing this on an exam, you're like, I can't picture it, so you have to rely entirely on the algebraic scenario. But when you can, what we're seeing pictorially, and hopefully we're convincing ourselves before we start, because we're practicing, it looks like I have a local minimum there. And that's what's going to happen on the surface. And we want to say that that's a local minimum for my surface, and then it goes up from there. And again, my picture, I did an okay job, but still, I don't know if that's exactly where it's supposed to be, or we can't rely on the picture always. We rely on these. Step 1, I compute the domain of my function. It's a polynomial of 2 variables, so the domain is R. So that means every point is an interior point of my domain. Now, if I take the first order partial derivatives of my function, I get fx is 2x and fy is 2x minus 4. Those are also polynomials and 2 variables, so quickly what my check is and why I write it down is they exist everywhere. Remember, Fermat says I want a critical number if it doesn't exist, if these two don't exist, or if they're 0. This step is just said I don't have to check any critical numbers where the partial derivatives don't exist, because they always exist. Now all I have to do is focus on step 3, where are they 0? The derivatives are 0 if and only if 2x is 0 and 2y minus 4 is 0. That gives me, solving this equation, that gives me x has to be 0, and solving this equation tells me that y has to equal 2, and that will give me the single point 0, 2. Now that's the only critical number for, or critical point now, not number because it's two-dimensional, for f of x, y. Now what Fermat's theorem says is if you don't have a critical number, there's no local max or saddle points anywhere. Because the saddle point has to be a critical number first. And that means that we're not going to have a local max min there. If we have a local max min first, you have to be a critical point. But not every critical point is a local max min. Ours is. How do we check that, or how do we argue that it's the saddle point? That's the last step here. And so how do I know that this is a absolute minimum or a local minimum? All I need is local right now. Why is this a local minimum or an absolute minimum? What we have is we have x squared, our function x squared plus y squared minus 4y plus 9 is actually equal to x squared, actually this is hidden, 9 is 4 plus 5, minus y squared minus 4y plus 4 plus 5. This is a completed square, which is now everything will be positive. By moving to completion of squares, I can say everything's larger than this. Yeah, so now I have x squared plus y minus 2 squared. Now I don't care what y is. He's squared, it'll be positive. I don't care what x is. It will be squared, it's positive. Positive, positive, plus 5. This is greater than or equal to 5 always on my domain. I don't care what these are. They're going to be positive, even if they're both 0, or if I get both zeros here, I'll get equal 5. It can only be larger than this. It's definitely strictly larger than 0, but specifically, I see that, what does that tell me? That tells me that f of x, y is equal to x squared plus y minus 2 squared plus 5, which is greater than or equal to 5, which is f of 0, 2. If I check and I put 5 in there, is that what I get? If we're actually going to check that, what is f of 0, 2? F of 0, 2 is equal to 0 squared plus 2 squared minus 4 times 2 plus 9, which is 4 plus 9 minus 8, which is 5. What that says is this was the critical point for my function. The maximum value, or the max or minimum value, or the critical value is 5. And now we saw that for every point in our domain, f of x is greater than or equal to 5, which is f of 0, 2. So what that says is, in our inequality, we're trying to match the definition. That's what we're essentially trying to say. Now I've shown that f of xy is greater than or equal to f of 0, 2 for every point in my domain. So that says not only is it a local max or a local minimum, it's also an absolute minimum. And this is how we're going to do this. So again, how do we recap this? In 1, I find the domain. I find the domain globally to worry about whether it's, I'm going to switch to arguing whether it's a local maximum, or whether I want to know whether it's an absolute maximum or a local minimum or an absolute minimum. So I find the domain first to find out where I could possibly have critical numbers. Then I take the first partial derivatives and see if they exist everywhere, or possibly they don't, or find out where there's 0. That gives me all my critical points. I have one critical point in this scenario. One critical point says now I have to find out whether it's a local maximum, a local minimum, or a saddle point. If it's a saddle point, then you're done. If it's a local max or min, you can also think to yourself, is that an absolute maximum and an absolute minimum? And I have to phrase that on my entire domain. So that's what we just done here. So in the last step, technically what I did was I showed that for my only critical point, I do in fact have that it is a local minimum, because near 0, 2, you're greater. But I also check on my domain. This statement is true for every point in my domain, so it's an absolute minimum for this function. All right, for our second example, the first one had a local minimum. Ideally, we would do one that has a local maximum too, but in this video, we don't want it to run too long. So this one, surprising magic, I already drew the picture so you can see it's going to have a saddle point. What are we talking about saddle point? The saddle surface is the one that we start off with. This is the hyperboloid of one sheet, or one of them anyways. What do we check? We check the domain. Again, it's a polynomial in 2 variables, so we have the domain is r squared. Then when I check, I find the first partial derivatives. Because this was polynomials, the first partial derivatives are also going to be polynomials in x and y. Therefore, they always exist. So there will be no critical points where the first partial derivatives don't exist. When are the first partial derivatives 0? That happens only when x is 0 and y is 0. So the only critical point we get for our function is 0, 0. And the value of our function at 0 is also 0. We've got a bunch of zeros everywhere. Now, the last stage is, so step 1 is find your domain. Step 2 is find out where your first partial derivatives exist or are 0. And then the last thing we want to know is, once we have all those critical points, we want to know whether they're a local max, a local min, or a saddle point. And then you have to argue inequalities in calculus, and if there are expressions involving 2 variables, so this isn't fun at first. But for these functions, we've made it simple enough for myself to notice that if I just like when we do limits, if we approach different trajectories, if I approach along the x-axis, my function will be negative x squared, where regardless, I don't even think it has to be the positive x-axis, regardless of what x is, when I square it, it'll be positive, and then the negative will give me less than 0. What that says is at 0, 0, there's points in any disk centered at 0, 0. There will be points in that disk which have values which are less than f of 0, 0, and there will be points in there, if I go along the y-axis, where the points have values larger than 0, 0, f of 0, 0, and that says that this is in fact a saddle point, or the point 0, 0, 0 is a saddle point for the surface S, which is the graph of this function z equals y squared minus x squared. Good. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones.